We shall continue with the nuclear and particle physics. So, last class we have been discussing about nuclear reactions. Now, we will proceed further to discuss nuclear reaction rate and what do you mean by Q value of a reaction, how to estimate that, and what is the importance of Q value, and we will discuss types of fission. So, for the reaction rate, we will just work out a problem to show how it is important. So, already we need to remember that geometrical cross section is pi r squared. So, based on that we are going to work out a problem. See, for pi r squared, derivation is one part, but what we can assume is the cross sectional area. What is the cross sectional area? Suppose I have got a sphere, nucleus is a sphere. If I got a sphere, and what will be the shadow? If you get the shadow will be only pi r squared. The nucleus is spherical, but the shadow will be circular. So, the circular radius will be pi r squared. So, it is also called shadow cross section or geometrical cross section. So, it is equal to pi r squared. Each nucleus is presenting an area of pi r squared towards incident particle. So, based on that we will work out a problem. A high energy neutron beam of flux 312 barns per second bombards Xe126 nucleus for production of radioisotopes, maybe for medical purpose, etc. We are assuming that R naught radius constant is 1.2 Fermi. We are asked to estimate the rate at which nuclear reaction will take place. Now, first point is we take it as sigma equal to pi r squared, that is the cross section pi r squared, and r equal to r naught a power 1 by 3, that we know from liquid drop model. The radius is r naught a power 1 by 3, where a is mass number of the nucleus, and here r naught is 1.2 Fermi. Therefore, the radius we are just substituting 1.2 into 10 power minus 15 into that a is 126. So, 126 power 1 by 3. So, if you calculate, you will be getting a 6.016 into 10 power minus 15 meter, that is the radius. Now, we will go for the cross section, that is, this is the radius. So, sigma will to pi r squared. So, I have to just substitute that. So, here sigma r, that is the r refers for reaction cross section. Sigma s will be for scattering cross section. This is for reaction, because we need to calculate the reaction rate. So, this is a pi into radius squared, we are writing this. So, this comes out to be 113.6 in 10 power minus 30 meter squared, and we are just shifting the decimal point and we are making it 10 power minus 28, because 10 power minus 28 meter squared will be corresponding to one barn. Therefore, this 10 power minus 28 is written, and that is written as barns. So, that is a conventional standard way of expressing the nuclear cross section. So, 10 power minus 28 is taken as barn. So, sigma r equal to 1.136 barns. Now, this is the cross section. Now, what is asked is number of reactions that will take place. Now, here number of reactions that takes place is proportional to flux V, the incident flux, the neutron flux. If it is coming at a larger velocity, or number of flux is nothing but number of neutrons crossing per unit area per second, and if it is a large beam coming out, then naturally reaction will be larger, and that proportionality constant is the cross section sigma r. Now, this nr equal to this already we have worked out, and this V flux is a given data 312, that is the given data. Therefore, we are able to calculate the number of reactions that will take place, 354.4 per second. So many reactions will take place. What we are able to find out is, for example, for production of radioisotopes for a scientific purpose or medical purpose, we need to know how many reactions will take place in 1 second. So, here according to our calculation, about 300 and more reactions will take in 1 second. So, thus reaction cross section is a valuable information for production of radioisotopes. So, we need to know, suppose we require so much of radioisotopes, how many hours or how many days it has to be under the beam, neutron beam. So, thus reaction can be studied. So now with this just one numerical example, we will be able to understand what is the importance of reaction cross section. Now we will go to the next one, Q value of a reaction. So already this generally in alpha decay, beta decay, everywhere we get the Q value. Q value is only the difference between the binding energy difference between the parent and daughter, or mass difference between the parent and daughter. So both will be same because the decrease in mass is available as increase in binding energy. So when there is parent will have a larger mass than the daughter products, and the daughter products will have greater binding energy than the parent. So the mass decreases and binding energy increases. So both are balanced. That is from Einstein's mass energy relation. Mass is only manifestation of energy. So when the mass decreases, energy will increase. So now we will just see, and the difference in mass of the parent and daughter products is the Q value, or difference in binding energy between the parent and daughter products is the Q value. That will also be the difference in kinetic energy of the parent system and the daughter system. When I say daughter system, daughter plus the particle that is emitted before and after, kinetic energy before and kinetic energy after. So all will be same. Therefore, from the kinematics of reaction, we will just write the kinematics of reaction. So M1 plus M2 becomes M3 plus M4. This is one nucleus, another nucleus becomes some other nucleus plus some other nucleus. So we are talking about the M1 here. We are just writing M1 as the light particle. So one is a light particle, for example neutron is bombarding a uranium target. So the light particle is neutron, the heavier particle is uranium. So here we are considering M1 as the light particle which is travelling, and M2 is the target nucleus, it's stationary. So one of them will be stationary and the smaller particle will be travelling. So this is the target nucleus, you write as M2, that is a stationary nucleus. M3 is the outgoing particle. So after the reaction, one particle will be coming out, maybe the neutron, and then after that maybe alpha particle comes out, some particle will be coming out. So M3 is the outgoing particle, and M4 is the product heavy nucleus. After the reaction, there is a heavy nucleus which comes out. For example, if you take uranium 92, 238, and neutron is bombarded, it becomes 239, and then we get one particle, maybe neutron is coming out and heavy particle will be there. Therefore, we are just talking about M3, M4, the product heavy nucleus. For example, if you take uranium, it will have krypton and barium which are fission process. Therefore, both will be outgoing particle and both will be having kinetic energy. When they move out, both krypton and barium will be having kinetic energy. Applying mass energy relation, that is Einstein's mass energy relation. So what we are writing is that we wrote just M1, M2, M3, M4, that is a reaction we wrote. Now as far as the incident particle is concerned, it will have, what is this M1 C squared, that is the rest mass energy. Rest mass energy of the incident particle, mc squared. Here it is M1 C squared, that is Einstein's relation. And this is rest mass energy, and this is the kinetic energy which it is bombarding. Kinetic energy, because it is not stationary, it is having kinetic energy E1. Then this is the second particle, here we write as M2 C squared, that is the rest mass energy. And here we do not write E2 because we have already assumed the target it is stationary, and therefore it does not have any kinetic energy initially. After the reaction, we get M3 C squared, that is M3 is the outgoing particle, M3 into C squared, that is the rest mass energy, plus it will be having kinetic energy which is E3. Similarly, we have got for M4 another particle or the heavy nucleus, byproduct nucleus, M4 C square, rest mass energy and kinetic energy. See here we take kinetic energy later also, because once the particle initially it is stationary, target is stationary, so we do not get that kinetic energy part, and the incident particle is there. After reaction, the outgoing particle will have kinetic energy, and this heavy nucleus will also have kinetic energy because of the recoil. It will have kinetic energy because of the recoil. It is like a bullet and gun. Bullet goes with a larger velocity, that is a light particle, but the gun is now stationary. The gun will have a recoil. Therefore, both will have kinetic energy. Therefore, we get this equation. Now, after that is only simplification. So, what we are doing, we are taking all the mass on one side, M1, M2 and M3, M4, all the M factors are brought this side, and C is a common factor, we take it out. So, we get M1 plus M2 minus M3 plus M4 into C squared, that will be equal to all that kinetic energy we are taking to the right side, E3 plus E4 minus E1, that is it. Now, what is Q? Q is nothing but change in kinetic energy, or it is also equal to change in mass. Both are same, because the kinetic energy is available because of the change in mass. That is already, according to Einstein's relation, the energy is only manifestation of, the mass is only manifestation of energy. So, then when there is a decrease in mass, there is increase in kinetic energy. So, we get this. So, the Q, we require expression for Q. So, the Q is change in kinetic energy. So, I can write Q is, what is the change in kinetic energy? This one, E3 plus E4 minus E1, that is the change in kinetic energy. This is after, kinetic energy after the reaction, E3 plus E4, and before the reaction we get minus E1, that is the incident particle. So, this is the change in kinetic energy which we write here, and that is also equal to change in mass. So, the change in mass we write this way. So, this part is change in mass. This is the initial mass M1 and M2, and this is the final mass M3 and M4. And what you need to remember is the mass, the initial mass will be larger because there is going to be decrease in mass. The initial, this is the initial mass M1 plus M2, and this is the final mass M3 plus M4. So, this minus this, that is the Q value. Of course, the C is there. So, we have just taken out C squared minus E squared. So, this is the expression for Q value in terms of kinetic energy and in terms of mass. Therefore, what we see is decrease in mass gives increase in energy, and mass is only manifestation of energy. So, it is only mass decreases and energy is appearing. The reaction will be possible. Theoretically, we need not do the experiment. Theoretically, this is a tool, just we find out whether such a reaction is going to be possible. It will be possible only when Q is greater than 0. Only when the Q is greater than 0, any reaction becomes possible. That is what here, this one, this must be larger, Q is greater, which means the initial mass must be greater than the final mass. Then only that particular reaction becomes possible. Now, we will just we'll discuss about the fission and fusion. This also comes under, it can be studied as a separate heading or also under nuclear reaction, because the fission is a reaction and also fusion is a both a reaction. Now, we will just outline where do you get this fission and fusion, or in what types of elements such a thing is possible. So, this curve is a binding energy curve. This is B. So, here we got binding energy per nucleon, which is in the x axis and in the A, mass number A, and here this is binding energy per nucleon in the y axis, and this is an experimental curve. This is the nature provided by nature, experimental curve. So, as A mass number increases, this goes on increasing and it is almost horizontal, and then it decreases. This is the nature's work. And here, which means these nuclei here with A equal to intermediate mass. Intermediate mass will have greater binding energy, like iron. So, it will have a greater binding energy, and these are all light nuclei like hydrogen, helium. They are all light nuclei. Binding energy per nucleon is small. Here again, when you go here, the binding energy slightly decreases after the intermediate stage, it decreases. So, how do you account for this? This is decreasing because as the nucleus becomes bigger and bigger, the proton repulsion will take place, because the binding occurs because of the nuclear attractive force, nuclear forces, attractive forces which are short range. Therefore, they are well bound, and as the nucleus becomes bigger and bigger, the Coulomb repulsion will also take place, and that is not short range, that is at all ranges we get. Therefore, this short range force, after when it becomes the nucleus becomes bigger, the Coulomb force dominates, and therefore the size becomes small. The binding energy per nucleon becomes smaller and smaller, and we can't get very heavy nuclei. That is why we are not able to get very heavy nuclei. So this is the region we have. This region will be like iron, etc. This will be like hydrogen, etc. Light nuclei, and this will be uranium and transuranic elements, all heavy nuclei. They are called actinides, those about 200. So this is the situation. Now here we talk about fission and fusion now. When you talk about fission, this because it is already unstable, they will have a tendency to split. Because of the Coulomb repulsion, they will have a tendency to split, and the heavy nucleus behaves like a liquid. It is coming under liquid drop model. So heavy nucleus, it's like a water drop, liquid drop, and if you have a water drop and if you slightly disturb it, it will split into 2 or 3 droplets. If it is a solid sphere, it will not can't break it easily. So here in this region, it is like a solid sphere, and when you go for a heavy nucleus, it is behaving like a liquid. So that is called liquid drop model, liquid, and therefore it will undergo fission. It will make 2 droplets. When it makes 2 droplets, a heavy nucleus with maybe mass number 200 will split into 100 and 100, maybe approximately 100 and 100. When it is 100 and 100, what will happen is the resulting fragments will fall in this region. So here this is 200, roughly about 200. Now when it is undergoing fission, the mass number will split as 100 and 100. Both the fragments will be here. So the binding energy has increased in this process. So the fission is taking place only because the binding energy is increasing. So any system, this reaction is possible only when the binding energy increases. That is for any system. Any system will try to move towards a greater binding energy. So suppose I have got a stone, or you think about maybe a slope, rocky slope. If you put a small stone there, and if you disturb that stone, it will come towards the earth. Because as it comes towards the earth, it is more and more binding, because it is attractive force, binding energy. Binding energy is more towards the earth, so it will move towards the earth. So when it is far away, if you slightly disturb, it will come here, and all of them will be gathering at the lower bottom. So the lower bottom will be maximum binding energy. Similarly, here we have got, this is the lower binding energy, it will move towards greater binding energy. So that is the natural process. It can't move in this direction. It can move only in this direction. Similarly, when you go for fusion, here the binding energy per nucleon is small. So they will try to bind one another. So when they bind together, they will make a bigger nucleus. So they will climb up the binding energy curve. Finally, they will be attaining this region. So here fission will give fragments of this region, and in fusion, these lighter nuclei will fuse up and go up in this region. So this is what happening. This fusion is happening in sun and stars. We get thermonuclear reactions. This is the source of energy that we are getting, sunlight, the source of energy for sun and also other stars. The source of energy is fusion. Fission energy in a reactor, we have got that fission energy, like in Kudankulam, and we have got so many Indian reactors. All of them are undergoing fission reaction. Now we will go back to the further explanation. So the fission, as we have been explaining here, now fission is nothing but splitting of heavy nucleus. That's what we have said. Example, 200 becomes 100 and 100. Here, example, uranium. We are not writing the isotope, it's just generally uranium becoming barium plus krypton. Barium and krypton will be in this region. They will have greater binding energy, and compared to this uranium. So there is increase in binding energy, and therefore as a result we will have energy release. So that decrease in mass, increase in binding energy. So that will give you a energy release. So you have to write as plus energy, some energy will be there. Now what are the types of fission? First going into fission, then we will go to fusion. One fission is called spontaneous. As the word says, there is no need for extra by itself. Spontaneous by itself, happening by itself is spontaneous. So that is called spontaneous fission. Other one is induced fission. So you have to trigger it in order that fission occurs. So here induced fission, it is induced spontaneous, it happens by itself. When you say induced fission, it can happen by you have to send a neutron or even X-ray or gamma ray. So we have to just send some energy, trigger it so that this fission will occur. So one is spontaneous, the other one is induced. So when do you get the spontaneous fission? That is without giving any energy. Energy, it goes by itself. We find that in the periodic table, if you take, we have got from hydrogen, we have got the periodic table Z equal to 92, 93, etc. Now Z equal to 92 is the uranium. Up to that we have a nature. After 92, 93, 94, 95, 94 for example is plutonium. Those and Z equal to 100 is fermium. Those elements are not existing naturally. They are only byproducts of nuclear reactions. Byproducts they will. So what will happen? Up to 92 we have got existing. If you take more than 92, it will undergo fission spontaneously and therefore they are not existing. For example, fermium 100, if it is produced, it will without giving any energy, it will undergo fission spontaneously because it is unstable spontaneously. Similarly 93, if you take neptunium 93, that also it will undergo fission spontaneously. That is why we don't have neptunium in the, if you remember, we had that radioactive series. The neptunium is called missing series. If you take 92, it is stable, it is available in nature, and that is the most unstable element available in nature. It is like it is on the rock, it is at a crucial point. Any disturbance, it is ready to come down, the stone will be coming down. So it requires some disturbance, small disturbance. That disturbance is called induced fission. So this is for all transuranic elements, and this is uranium and maybe thorium, slightly less than uranium also. And we will be getting induced for thorium has got Z equal 90, or you take uranium 92. These things are critical. Therefore, we have to give some energy. Whereas if you take fermium Z equal to 100, it will undergo fission spontaneously. Now, as we are just telling what is the energy to be given, that is called critical energy. What is critical energy? Critical energy we denote as EC, E suffix C, critical energy. That is the energy required to initiate fission in a nucleus. What is the energy required to initiate fission? So, EC, that critical energy, is more for light nuclei. For example, if you take calcium 2040, if you remember, calcium 20 has got proton number 20, which is a magic number, and 40, that is neutron number is also 20, which is a magic number. So we get 20 is a doubly magic nucleus. It is a very stable nucleus. It is a light nucleus because the mass number is only 40, light. So if you want to split that, we have to give large energy. It is possible. You have to give large energy to split. Maybe the 40 will split as 20 and 20. It is able to, we can split, but the energy required will be more. EC will be more for light nuclei like calcium, magnesium, all that, or iron, all that will be, we require large energy to disturb it. Now EC is small for AV nuclei. Already we have been discussing, because it is already in a disturbed fashion because of the excess proton. Because of the proton, it is already having Coulomb repulsion, and therefore EC will be small for AV nuclei. Example will be uranium, and EC will be 0 for super AV nuclei. When you say super AV nuclei, that is transuranic. See, as the word says, after transuranic, after uranium. So uranium has got 92. Anything after uranium is called transuranic element. Now, how do you, this critical energy, this was studied by Bohr and Wheeler, and they have derived one expression, and that is Z squared by A is greater than 48. That is an expression they have derived. We did not derive that, but we will be just recalling the final expression. This is the condition for spontaneous fission. So, if you have a nucleus with the Z squared by A greater than 48, such a nucleus will not exist in nature, because it will undergo fission spontaneously. So, any nucleus which is available in nature will have Z squared by A less than 48. This is the condition. That is the test. Which nucleus you will be using for a reactor, we have to take this as a check, and the Z squared A must be maximum for a to be used as a fuel in a reactor. And here just we will talk about natural uranium. It has got 235 and 238, and only 0.7% of 235, and 99% will be uranium 238, and 235 requires slow neutron. When you say slow neutron, it will be in EV. When you take uranium 238, it will have fast neutron which will require MeV energy. What you remember is 235 will require slow, 238 will have fast neutron. Neutron emission. So, when you take uranium 235 plus slow neutron, these are the possibilities: XR plus Xe plus 2 neutron, or Kr plus Ba plus 3 neutron. So, here one reaction gives 2, another gives 3. There are so many channels possible, and average they found that it is 2.5 neutron. Discuss further on fission, and here we will just wind up for the day. So, we will just summarize. We have discussed reaction rate and worked out a numerical problem for reaction rate. Expression for Q we have derived, and we have discussed the types of fission reactions. And just a few questions for the day. Explain how reaction rate can be estimated from the reaction cross section. Derive an expression for Q value of a reaction. Outline the types of fission reaction. Thank you.